Hey guys, welcome back to another RASK Maths video, and in this video I'm going to be talking about where the binomial distribution formula, which you see here, actually comes from. So, before we get into this video, you should know about binomial distribution, which is basically just a formula which gives you the expansion of any sort of binomial. So if you have something like x plus 1 to the n, you can just say this is going to be, actually I'll do the general case since that's better. So if we have the expansion of a plus b to the n, well, the binomial expansion just tells us that this is equal to, if we set r equal to 0 to n choose r times a to the r times b to the n minus r, like so. So this is the binomial expansion formula, and you know it can be proved with things like the can actually be proved with the derivative power rule, Taylor series expansions, things like that. But yeah, I've actually talked about this slightly in the previous video, so do a bit of research on this if you're not familiar. But I'm going to be using this to show how you get to this binomial distribution formula over here. So before we get started, I'll just explain what this actually means. So x is going to represent a sort of number. So it basically represents the number of successes within n trials. So for example, if we were doing something like if we were throwing dice, so if we were throwing 6 dice, well, 6 die, then n would be 6, that's the total number of trials. And if the probability of getting a, let's just say it wasn't a fair die, so if the probability of getting a 1 was 1/3, then p, the probability of success, is 1/3, and x is the number of ones thrown within those 6 dice throws. So you can work out the probability of getting, let's say, 3 ones. So if you set x is equal to 3, like so, we can work out that probability using this formula. So n choose 3, p, which we set as 1/3, to the x times q, which is just 1 minus p, so the opposite of p, times n minus x, so the remaining. So I'll show you guys how we get to that. Now, let's go over here. So first of all, let's set up our situation. Let's use the dice, for example, as shown above. So let's say we have a biased dice has a 1/3 chance of landing 1. So like this face here. So it has a 1/3 chance of landing 1, and we want to calculate the chance, the probability. Let's say calculate the probability of throwing 3 ones. I'll just put the dice face in so it's easier to understand, because otherwise it might be a bit confusing. So we want to calculate the probability of throwing 3 ones. So I'm going to do this in the regular sense. Now, obviously, and let's say out of 4 dice. Actually, I'll say the probability of throwing 2 out of 3, since that'll make drawing the later diagrams a bit easier. So let's now start by giving a few variable names. So let's start with p, which is going to be the probability of throwing a 1. And this is just equal to 1/3, as we've shown above. And now we're going to have to get a q, which is just the inverse. So let's have q. Well, this is the opposite of 1. So we'll just set this to be 1 minus p, or in this case, if this was the true, then this is the false case. So see, that's where the by comes from. It's either true or false. So q is 1 minus p, so it's basically everything else. So like throw in a 2, 3, 4, 5, and 6. And this is just going to be 2/3, since p was 1/3. So now we can actually get started with the tree diagram. Now, if we start over here, let's say this is the first row out of 3. So we can either get a 1, like so, everything else. And the probability of this is P and Q, like shown. Now, on second row, we can get this, and we'll get either a 1 or we'll just say not 1, like so. And actually, that's probably a better thing to write here as well, since it makes a bit more sense. So it's either getting a 1 or not a 1. It's important for binomial distributions to only have 2 possible outcomes. So again, the probability of this is P and probability of this is Q, because hopefully that makes sense. P is literally defined as the probability of throwing a 1. And we will just do this one more time. I'll just put some ellipses here since it's the same sort of thing, but just repeating. So we can either get a 1 or not a 1. So these are our 3 throws, and they've been represented in the tree diagram. Hopefully it's not too confusing. I'll just rule this off. Okay, so here's our tree diagram, and this is meant to represent our possibilities. So you see we've got 3 throws if you extend out this tree diagram, and we want to calculate the probability of throwing 2 1s. So you basically can either go this route, like so, we can go like that would give us 2 P's. So right over here, this route is going to give us P squared times Q. That's what's going to be the outcome, like the probability of this, because we go 2 along and then down there. You can see this is going to be P cubed, like so. But you can also should notice that there's other ways of throwing 2 out of 3 1s. So we could go, for example, P, Q, and then P, like so. Although I haven't drawn it in, but this is also another possible route. And there's another P squared Q, like so. So you can see there's going to be lots of P squared Qs, and we basically want to calculate the total probability of all of these. Well, luckily for us, we actually know, if you notice now, we've got P cubed, we've got P squared Qs, and we also have other probabilities, like if we have PQQ, well, that's also going to give us, just put it down here, we'll get a PQ squared, and if we go QQQ, that's going to give us a Q cubed, like so. So you can see we've got lots of different, I'll call it classes of probabilities, and there's multiple ways in which they can happen. So we want to effectively find a formula which is going to give us the total of this without having to manually go through each path. And luckily, we actually know a formula for that. So we can represent our situation, this entire tree diagram, using a binomial expansion. And let's just say this can come out to be P plus Q, and we're going to expand it 3 times. So what you'll notice is if we expand this 3 times, I can just show you guys what this is going to be. So we'll get P cubed plus 3P squared Q plus 3PQ squared plus Q cubed, like so. This is the expansion of that, and this is also what's going to happen if we expand out, if we calculate every single possibility from this tree diagram, because there's actually 3 ways in which we can get P squared Q. We can go PPQ, PQP, or QPP, like so. And there are 3 ways. So we've managed to simplify this entire tree diagram into a simple binomial expansion. And hopefully you can see now, this can be generalized into, if we have any situation, we have P plus Q to the n, then this is just going to be the binomial expansion of this. So NCR p to the r, q to the n minus r. This is literally just going to be the binomial expansion of this. And p and q, so p represents the true, the like 1/3 in our case, the probability of getting a true outcome, so the one we want, and q represents everything else, so the false outcome. And we're basically just going through the tree diagram n times. So if n was 1, we'd stop here. If n was 2, we'd stop here. And if n was 3, we'd stop there. Like so, and it just carries on indefinitely, how many trials you want. And yeah, now you can see it's pretty easy. So if we want to calculate how many times 3, or if we go back to the original question, calculate the probability of throwing 2 1s, well, we know the probability of one of getting a true or hit is given by p. So if we just want to get 2 1s, we can look at this term on its own, like so, and this will give us the probability of getting 2 1s. So you can see this entire thing is going to add up to 1 because p plus q is going to add up to 1, and 1 cubed is just equal to 1. So we know this is equal to 1. So if you want to work out the probability of just, if we just get this value, this is going to be equal to the probability of getting 2 successful hits. So from there, you can see we can actually generalize this even further. Now we can write x is our number of true, I'm not sure the right word, let's just say, let's say number of successes, that is better. So number of successes, and in this example, a success is throwing a 1. So x is the number of successes, and you can say x is modeled by the binomial distribution, that's just what this B symbol means, of n trials. So in this example, n is 3. There were 3 trials, or 3 rows, or 3 columns in that tree diagram. And we also want to give the probability of getting a success. So probability of success, in this example, it was 1/3. So once you've modeled it with the binomial expansion, you can see how we can calculate the probability of getting an x, like let's just say x equals, don't want to use small x because that's a little confusing. So I'll use the probability that x is equal to a, we'll just say that. So that's given by, well, the probability x is equal to a is the same as, this is the same as finding the p to the a term. And of course, since you know the exponents of this always have to add up to n, because you're always going to just go a total of n columns, so the exponents have to add up to n. Like you can see, this is 3, this is 2 plus 1, this is 1 plus 2, and this is 3, so they always have to add up to this original n. So you can see finding the PA term, well, therefore that's going to also mean we have to find a PA QN minus A term, because when you add these together, that just gives you n. Oh, sorry, n, like so. So that is find this term, and then it's just going to come with its own coefficient, and that's the coefficient which really matters, because you can always just work this out quickly, but it's the coefficient which we really care about, and that's given by this NCR term over here. So hopefully that makes sense why you can now see we have the original NCR term. So the probability x is equal to a is equal to NCR, or NCA, times p to the a multiplied by q to the n minus a. And that is where this binomial distribution definition comes from. We're basically trying to find this NCA constant gives us the number of times this p squared q, or whatever term we're looking for, comes up in this tree diagram. And then of course we do need to multiply it by the original probabilities, which in our case would be as simple as just plugging in values of P and Q as 1/3 and 2/3 respectively. So yeah, hopefully you guys could keep up with that, hopefully, and I hope you understand where this binomial distribution formula comes from. It's all to do with this tree diagram and having P, just counting the number of successes and then sort of working out the coefficients using binomial expansion from there. Thanks for watching, and I'll see you guys in a future tutorial. Bye.